Welcome to the Deep Dive, where we take a complicated stack of sources and distill it down into the essential knowledge you need to be well informed. Today, we are talking about a truly critical intersection, the deployment of artificial intelligence inside the systems that control our physical world, operational technology, or OT.
It really is the critical nexus, and the pressure right now is intense. I mean, ever since generative models like ChatGPT hit the mainstream in, late 2022,
Right?
AI has just moved from this theoretical concept to a business mandate. And now we're seeing machine learning models, even large language models, being pushed into these vital systems.
But we're talking about power grids, water treatment plants.
Manufacturing, traffic control, all of it.
The potential benefits are they're undeniable. You see incredible efficiency, predictive maintenance that saves millions, faster decision-making. But, and this is the big but, if you connect an AI that might, say, quietly drift in accuracy, or worse.
Or hallucinate a false reading.
Exactly. You connect that to a piece of physical infrastructure, and the risks become genuinely existential. We're talking process drift that leads to equipment failure, unintended safety process bypasses, and, the potential for actual physical harm.
Precisely. And that is what makes our source material for this deep dive so extraordinary. This isn't just one company's opinion or one government's guidance. We are analyzing joint guidance published in December 2025 that represents a global consensus.
What's the global consensus? Who is involved?
It was co-authored by 9 major international cybersecurity and intelligence agencies. We're talking heavyweights like CISA, the NSA, the FBI.
Okay, wow.
The UK's NCSC, the Australian Signals Directorate, and their counterparts across Germany, Canada, the Netherlands, and New Zealand. When 9 global leaders align on risk mitigation like this, you know the threat is serious.
That level of international collaboration is almost unheard of for a technology rollout. So our mission today is to walk you through the 4 essential principles these agencies have outlined for critical infrastructure owners and operators, for you to safely and securely integrate AI into your OT environments. But first, let's do a quick language check. In this world, definitions are everything.
They absolutely are. We need to be precise. The guidance defines artificial intelligence, or AI, quite broadly. It's basically a system using inputs to make predictions, recommendations, or decisions that influence real or virtual environments.
So it covers a lot of ground.
A huge amount. From complex ML models to agents.
And then we get to a distinction that gets confused all the time in the technical world. Safety versus security.
And that confusion is so dangerous in OT. Safety, or functional safety, refers strictly to preventing physical harm, to people or to property.
So systems managing the flow of water, the pressure in a pipe, traffic lights.
Exactly. Security, on the other hand, or cybersecurity, is that traditional triad we all know. Confidentiality, integrity, and availability, the CIA of data and systems.
Right.
In critical infrastructure, you can lose data. That's a security failure, and maybe be okay. But if you lose physical control, a safety failure, people can die. The guidance just hammers this point home. AI has to address both simultaneously.
Crystal clear. Before we jump into Principle 1, Understanding the Risk, we want to take a moment to thank our partners who make these deep dives possible. A huge thank you to CISOmarketplace.com and CISOmarketplace.services for supporting this deep dive into the absolute necessity of securing AI in critical infrastructure.
Okay, so let's move into Principle 1, understanding the AIoT risk landscape. What's critical here is that the guidance isn't really concerned with, simple automation or the statistical modeling we've used for decades.
This isn't about that.
No, their focus is strictly on complex systems, advanced machine learning, large language models or LLMs, and autonomous AI agents.
And where those models actually sit in the infrastructure, that fundamentally changes the security profile, right?
Yeah.
If we use the industry standard Purdue model for a minute.
Yeah, the hierarchical map of an OT network.
Right, from the physical devices at the bottom to the business network at the top, you see different AIs living at different levels.
Exactly right. ML models, so predictive algorithms for anomaly detection or maintenance, they typically live down in the operational layers, levels 0 through 3.
So they're close to the action.
Very close, often embedded right in the controllers. And that means they are subject to strict immediate safety controls. But LLMs, they live much higher up. Enterprise networks, levels 4 and 5.
And why does that distinction matter so much?
It means LLMs are typically operating on aggregated data that has already left the safety perimeter of the factory floor or the processing facility. They're used for high-level stuff like workflow optimization or behavioral analytics, far removed from physical control.
So the security model is totally different.
Completely. A level 5 LLM can be compromised through IT channels, and that could lead to decisions that impact level 3 systems, entirely bypassing your primary safety controls.
Okay, so let's unpack the unique risks that are either new or um, amplified by introducing these AI systems. I think the agency's focus on the risks of drift and hallucination is really compelling for OT environments.
They are such insidious threats. Let's start with AI model drift. This is where the model's accuracy degrades over time because the real-world operational environment, the temperature, the flow rates, the material properties, it's always changing. The AI was trained on old data.
So what does that actually look like on the factory floor? It's not like the system just crashes, is it?
No, and that's what's worse. A crash is immediate, it's obvious. Drift is subtle. It means your predictive maintenance system that was 98% accurate is now, say, 85% accurate, and it's quietly allowing critical equipment to deteriorate longer than it should.
So that slow, quiet degradation is incredibly dangerous in an environment that's always on.
Exactly. It directly reduces your system availability and, most critically, your safety margin.
And then you have the notorious lack of explainability. These deep neural networks are just black boxes. If the AI tells a control system to adjust a valve and that adjustment causes a near-miss safety incident, how on earth do you audit that decision?
That is the core challenge. Explainability makes troubleshooting, auditing, and functional safety verification extremely difficult. If you can't trace the why, the causal chain of logic, you can't certify the system as safe according to current regulatory standards.
And if you can't certify it, you can't legally deploy it in a lot of these critical systems.
You just can't.
That difficulty in auditing is what leads the guidance to make an incredibly definitive statement about the reliability of LLMs.
It is. They are very, very clear on reliability and hallucination. LLMs were designed to sound plausible, not to be factually accurate in a physical context. Their ability to hallucinate,
To just make things up.
to fabricate false but convincing data, that poses severe risks of unsafe operating conditions. The recommendation is stark. LLMs almost certainly should not be used to make safety decisions or directly influence control logic in OT.
Wow, almost certainly should not. That is incredibly definitive coming from 9 major global agencies.
Yeah.
That fundamentally restricts how we can deploy some of the most popular AI today. So we can use them to summarize status reports,
Sure.
but not for adjusting the flow of wastewater.
Precisely. If an LLM fabricates a pressure reading and a chemical process, that's not just a data error. It's a potential catastrophic safety failure that requires immediate human judgment to avert. The risk is just too high.
Okay, the final key risk from Principle 1 I wanted to touch on is the human one, AI dependency and skill erosion. We start to rely on the AI, and our operators lose that essential muscle memory for manual intervention.
This is a major concern. If operators become over-reliant, they might ignore valid alerts if the AI failed to flag them, or they might not have the manual skills to safely manage the system during a failure.
So you get skill degradation.
A huge degradation of core human competencies. It's an explicit mandate in the guidance. Operators must maintain operational competencies alongside the AI systems, not be replaced by them.
That's the balance, isn't it? How do you get the efficiency gains without sacrificing the core competency you need when the AI inevitably hits a wall?
It means training has to change. It has to explicitly include scenarios where the AI output is wrong, forcing the operator to use other sensors, raw temperature, vibration data, to validate the system's recommendation before they act on it.
Okay, with those risks understood, let's move to Principle 2. Considering the use case and the vendor role, this is where organizations are told to, step back before they sign any contract.
And subprinciple 2.1 is critical here. Organizations must first rigorously assess if AI is truly the best solution. You have to compare its complexity, its cost, its inherent risk profile against established, simpler, and more deterministic capabilities.
So adding complexity just because you can add AI is a recipe for disaster in critical infrastructure.
It absolutely is.
I love that the guidance gives a structured example of how to do this pre-deployment assessment. They use a fictional industrial generator predictive maintenance system. The problem is high downtime. The goal is to detect failures 30 days in advance.
Right, and that quantifiable goal leads directly to requirements. You need reliable detection, obviously, but you also need strict security controls. The aggregated OT data has to be protected in transit and at rest, and crucially, they introduce an operational constraint.
Which is?
Data aggregation must not exceed a performance metric, like, say, 80% network bandwidth usage.
Wait, hang on. Why is a network bandwidth cap a safety and security requirement?
Because if the AI system starts gobbling up the network with data aggregation, it starves other critical control systems of bandwidth.
Ah, so it creates a denial of service.
A denial of service that impacts availability and safety. If the AI system can't meet that network limit, or if its alarms cause operator fatigue, another explicit requirement, then it's just not the right tool for the job.
That's a fantastic practical insight. Now, what about the core data security challenges of actually training these models? That's in 2.2.
Right. We have to manage OT data security, especially when training is involved. This brings in data assurance and data sovereignty. You need to know exactly where your OT data is being stored and managed, especially if it's remote, cloud-based, or offshore.
Because if a vendor is based in another country,
Their operations are subject to foreign government control and laws.
so we're potentially talking about allowing another country to hold the keys to our core operational secrets.
Precisely. And those secrets live in two main types of data. First, engineering configuration data, network diagrams, logic, schematics, that's your IP. And second, ephemeral OT data, sensor readings like voltage, flow rates, temperature.
Stuff that's transient.
Right. But if it's used to train a model, it can become statistically accessible, exposing proprietary patterns of activity and how your facility actually behaves.
Which leads us directly to vendors. Section 2.3. As OT devices ship with built-in AI that might need internet connectivity, owners, you have to demand transparency.
Absolutely. Organizations must demand contractual clarity on the AI features and their data requirements. They need software bill of materials, SBMs, not just for the software, but to clarify the AI supply chain. Where are the models hosted? What foundational models do they rely on?
And I imagine demanding explicit data usage policies is just non-negotiable.
Correct. You have to prevent vendors from using your proprietary operational data to train their general purpose models. And critically, owners must maintain the contractual and technical ability to disable specific AI features if they're deemed unsafe or unstable.
It's a lot to ask of a vendor, but clearly necessary. This focus on clear requirements and risk navigation is why we're so grateful for the continued support of CISOmarketplace.com and CISOmarketplace.services in helping organizations navigate these complex industry challenges.
Okay, moving to Principle 3. Establishing AI governance and assurance frameworks. This shifts the focus internally, making sure the organization is structurally prepared.
So governance 3.1 isn't just about a committee. It requires buy-in from the very top. The CEO and CISO have to be involved, collaborating across OT, IT, AI subject matter experts, and the cybersecurity teams.
And that structure must establish clear roles and responsibilities. Without this, liability and operational confusion are guaranteed when an incident happens.
Who's on the hook?
Exactly. Is the OT team responsible for the model drift? Is the IT team responsible for the prompt injection? Clear data governance encryption, access controls, continuous verification has to be a core requirement of this structure.
And if we connect this to existing security practices 3.2, AI risks shouldn't be treated as some special isolated process. They need to be mapped into existing security frameworks.
That's where you update your existing tools. Cybersecurity teams have to incorporate AI-specific tactics, techniques, and procedures TTPs during threat modeling. You can't just use your traditional network intrusion threat models anymore.
So we're not just looking for a malicious actor trying to get in. We're looking for someone trying to poison the data set that the AI relies on.
Precisely. And that's why the guidance points to resources like the NRE Adversarial Threat Landscape for Artificial Intelligence Systems or the MITRE Atlas Matrix. It helps you anticipate novel attacks like data poisoning or evasion, and it ensures your security audits actually cover these new vectors.
And once the governance is set, we move to rigorous testing 3.3. What does that trajectory look like for an AI system that controls physical things?
You start small, low-fidelity testing for rapid iteration. Then you move to more realistic, non-production environments, including crucial hardware in the loop, or HI testing.
Where you test the software on the actual physical hardware.
Exactly. And while virtualization can speed some things up, you only move to full production after you've thoroughly verified that the AI meets its objectives without sacrificing functional safety.
This level of testing suggests a major headache for existing compliance and standards, which is 3.4. It's hard enough to audit traditional software for safety. how do you audit a black box?
It's a huge challenge. AI systems often struggle to demonstrate the auditability you need to meet stringent OT safety regulations. Owners have to continuously validate performance, and this is critical. They must identify and deploy specific thresholds for when the system has to immediately default back to a non-AI or manual system.
So you have to plan for it to fail.
You have to acknowledge the technology is not yet fully mature for these requirements.
Are there any standards starting to emerge that can help guide organizations here?
Yes. They mention specific evolving guidelines, like from the European Telecommunications Standards Institute, or ETSI, specifically standards TR 104-128 and TS 104-223. They're important because they're directly focused on the cybersecurity and operational requirements for AI models in networked environments.
That leads us perfectly into our final core principle for embedding fail-safes and human oversight.
This one's really the philosophical anchor of the whole thing. It emphasizes that humans are ultimately responsible for functional safety. The AI tools, they operationalize oversight, but the final legal and ethical accountability rests squarely with the people in charge.
So, human in the loop, or HITL, decision-making isn't optional. It's essential, especially for any active AI system influencing control logic. How do we build those critical intervention points?
For active control systems, you have to use safety thresholds, alternative sensor outputs, or state changes to create intervention points where a human operator must intervene. This ensures that human context is applied, enhancing reliability and maintaining human expertise. And a key actionable step for compliance and forensics is making sure AI decisions are logged with a distinct AI identity, separate from typical user IDs.
So you can trace it when things go wrong.
You know exactly who or what made the call.
And finally, the fail-safes themselves, 4.2. We have to plan for graceful failure in the design phase.
Absolutely. The system has to fail gracefully without disrupting critical operations. That means incorporating new AI system failure states
Like how to bypass or replace it.
into your existing functional safety procedures, and crucially, updating your incident response plans, your IRPs. If the AI fails, the IRP needs a clear step-by-step procedure for the human to take over safely and immediately.
And for systems integration, what kind of architecture does the guidance recommend to reduce the attack surface?
A key mitigation strategy here is prioritizing a push-based architecture.
Meaning,
Data should be pushed out of the OT network for analysis on the enterprise side. This avoids creating persistent inbound access pathways. You analyze the data outside the OT network, you maintain segmentation best practices, and you only push verified control changes back in through secure, controlled mechanisms. You limit the attack path.
this has been an incredibly rigorous deep dive into guidance that is setting the global standard for the future of critical infrastructure security. To summarize for you, critical infrastructure owners must first understand the unique and amplified risks AI poses, especially drift and hallucination. Then, rigorously consider the business use case and demand transparency from vendors. Third, establish robust governance and assurance frameworks, including testing against specific AI threat models like MITRE Atlas. And finally, embed fail-safes and mandatory human oversight, because ultimate responsibility for safety remains human.
Yeah, the consensus from these 9 agencies is a mandate for continuous monitoring, validation, and refinement of AI models to achieve a balanced, safe, and secure integration. And if we connect this back to the bigger picture, the entire conversation rests on this concept of transparency and explainable AI, or XAI. XAI clarifies why an AI made a decision, and transparency focuses on how the system works.
But the challenge remains.
Well, the source material notes that while these XAI techniques are rapidly evolving to help developers, it remains an open and very serious question whether these techniques are truly adequate for meeting the extraordinarily stringent safety and regulatory requirements that govern functional safety in OT environments today. That gap between AI's current capabilities and what regulations demand is where the biggest risk still lies.
And that question, whether model explainability can ever truly satisfy a functional safety auditor, is definitely something for you to continue mulling over as this technology evolves.
It's a critical area for future exploration indeed.
Thank you again to our sponsors, CISOmarketplace.com and CISOmarketplace.services, for enabling this deep dive into the complex world of securing AI in our most critical infrastructure.